Hello there and welcome back to another video. In today's video, I'm going to be building a custom solution for keeping track of the temperature of both my room and my server closet. Currently, my temperature monitoring system for my server closet is just this little temperature sensor that I got somewhere. I just set it on top of my rack to monitor roughly what the temperature is in the server closet. However, I don't know how accurate this device truly is, and I also don't love that I have to get up and open the server closet to be able to check the temperature. So I came up with an idea to build a wireless temperature measurement system with some microcontrollers and some nRF24 modules, which I then began designing. I started with the designing of what I call the base station, which the remote sensor will phone home its data to. The base station will have a small display and a way of navigating an interface to display the remote sensor's data, as well as the data of the sensor that's locally inside the base station, just to have a reference of the temperature at the desk that the base station will be positioned on. As for the exact components that I used for the base station, I chose an ESP32 as a microcontroller with the thought that it could possibly be integrated into something like Home Assistant by someone who knows how to do that. I then used a simple 128 by 64 pixel OLED display for the display, an nRF24 module to facilitate the wireless connection between the remote sensor and the base station, and a BME 280 temperature, humidity, and pressure sensor. There's nothing that's really special about the components I chose or how they're hooked up to each other, as the BME 280 and the OLED display are both just I2C bus devices, and the nRF24 just connects to the ESP32 with SPI. Then, I connected a rotary encoder to some of the other GPIO pins so that I could navigate the menus. As for the remote temperature sensor, it's an even simpler design than the base station's design. All that the remote sensor consists of is an Arduino Nano, another nRF24, and another BME 280. Since all this box will do is measure the temperature and humidity periodically and send the data to the base station through the nRF24, it doesn't need any special input or output interfaces, or even that powerful of a microcontroller. And with those basic schematics quickly thrown together, I was able to begin the process of prototyping out these two devices on some breadboards. And I actually didn't film most of the troubleshooting or prototyping for this project because I mostly just wanted to get it done as fast as possible. So here you can see the code working on both the base station prototype and the remote sensor prototype. The base station prototype is able to read its own sensor's data and display it on the screen. And when using the buttons to switch the data that the display was showing, it could show the data from the remote sensor, and from what I could tell, the readouts seemed to be quite accurate to what I would be expecting based on how warm the room was at the time of filming. Now, the one thing that some of you might have noticed is that the rotary encoder is nowhere to be seen here. And that's because I was having some very serious issues with getting the rotary encoder working. It would either be inconsistent and unresponsive, or the ESP32 would crash repeatedly from the amount of interrupts that it caused. So I actually ended up switching out the encoder for a simple 3-button interface, which I'm also not going to be fully utilizing right now, but I do want to leave room to make the menus on this device more advanced in the future, so I'll be giving it this full 3-button interface. But anyway, I finalized the PCB designs for the two modules and sent them off to the sponsor of today's video, PCBWay. PCBWay offers high-quality manufacturing services, such as CNC machining of many different materials such as aluminum, stainless steel, brass, and even titanium, which could be incredibly useful for making all kinds of mechanical parts in your projects. They also offer several different high-quality 3D printing processes so that you can print things in materials such as the notoriously hard-to-print nylon, specialty plastics such as PEEK, and even metals like aluminum, which I've actually used before to make some really solid mechanical parts in my lighting system. Of course, they also offer more common PLA and ABS printing, which can pair nicely with custom PCBs to make enclosures for your devices. Speaking of PCBs, PCBWay, as their name would suggest, also offers a very versatile custom PCB manufacturing service, which I've used in this project to get these beautiful custom boards, which I'm going to go solder the components to now. Thank you again to PCBWay for sponsoring this video and providing these PCBs to me for this project. I started by soldering the Arduino Nano, NRF24, and the BME280 to the remote sensor's PCB, though I did forget to solder on the 10 microfarad capacitor to the PCB before putting on the NRF24. Thankfully, I was able to just solder it across the 3.3 volt and ground pins on the top of the module, and this should work fine. I then moved on to soldering together the base station PCB, but even though this board connects to more components, I still only soldered the microcontroller, NRF24 with its capacitor, and the BME280 sensor. I left the pads for the OLED display, the buttons, and the power input blank so that I could connect jumper wires to them later, as these components aren't mounted directly to the PCB. But with most of the soldering on the two PCBs complete, it's time to talk about the enclosure that I made for these two boards. Starting with the remote sensor, as it's the simpler of the two, I'll be pairing my custom PCB with one of these little USB-C breakout boards in a super small 3D printed box that I designed and printed out of PLA with my 3D printer. Since I'm making this project completely available for you to build yourself, if you think it's something that you might want to make, I'm going to sort of enter into tutorial mode here while talking about the assembly of this part of the project. Mounting the USB-C breakout in this enclosure is actually really tricky, even though it's just two M3 screws that screw into the plastic enclosure. Although it's tricky, it is doable, so be patient if you're building this at home. Then, the main board can be mounted into the bottom of the enclosure, and while I was building mine, I discovered a small clearance issue that I had to remedy by modifying my board. However, the PCB files that I provide on the Instructable for this project have this issue fixed. After mounting the main board with just a single screw, as there's really no need to screw in all three, and doing so would be kind of difficult, I soldered the wires from the power in terminals on the PCB to the V-bus and ground connections on the USB breakout board. And that's actually all the main assembly for the remote sensor box. The only thing left at this point is to screw the lid onto the box with two more M3 screws, and we're done here. Connecting a USB cable to the USB-C port on the back of this box powers it up, as is evident by the Arduino Nano's power light, and this part of the project should be done now. To quickly test the remote temperature box, I soldered some female jumper cables to the OLED header on the base station's PCB and plugged the OLED display into it. I then powered it up and used another jumper wire to send a button press to the ESP32 so that I could make sure it was receiving the data from the remote box properly. Thankfully, the remote sensor box seemed to be working flawlessly, which was super satisfying to see. Now, for the main base station box, this one's a much more involved assembly process, as there are several more components to wire up, and still a pretty cramped box to do all of that in. The first thing that I did was solder some short cables to the pins on the three keyboard switches, so that I could connect them to the PCB later. I also soldered some of the same color wires to the buttons header on the PCB, and while you don't have to color code, I chose to do it for the sake of simplicity when assembling. I ended up using the color scheme of black for ground, and then three other colors, one of which for each of the three buttons. I then mounted the PCB into the case and soldered the connections between the power in header and the USB-C breakout board. I also then took the lazy method of mounting the USB-C breakout board into the chassis, as I didn't make this breakout board any easier to mount than the one in the remote sensor box. After that, I took the three keyboard switches and pushed them into their three mounting spots. And just as a side note, I'm super pleased with how this mounting structure for the buttons worked out, as my measurements were quite rough, but everything fit perfectly on the first try. Now, since I color-coded all of my wires, I took all of the black wires, those being the one from the PCB, and the three others with one from each button, and soldered them all together. Then, I soldered the other three colors of wires together to connect the buttons to the PCB. I then mounted the OLED display to the case with the help of 4 M2 screws and their matching nuts. And this was probably the hardest part of this entire project. If you can't tell yet, assembling these devices is certainly not for the faint of heart, but I will say that I'm still excited to get the end product working. After I mounted the OLED screen, I connected it using the jumper cables that I had soldered to the PCB earlier and gave the device a quick test. It received power from the USB-C port properly, got the data from the remote sensor correctly, and all of the buttons seemed to work exactly as I expected them to. So I closed up this part of the project with the 3D printed lid and some M3 screws, as well as some little caps for the keyboard switches, and finally I'm ready to give a demo of this little temperature and humidity monitoring system. The base station box is powered through the single USB-C port on the back of it and displays the data of both the temperature sensor inside the base station and the remote temperature sensor that sends its temperature data wirelessly to the base station. Also, the base station technically has Wi-Fi and Bluetooth capability as it's powered by an ESP32, so if you knew how to program it, this could absolutely connect to some kind of an app, or maybe even something like Home Assistant. Neither of those were functions that I personally wanted this device to have, so I didn't go out and learn how to program them. But if you're building this and you want them, you could totally figure out how to program that into the system. Although I didn't implement all of these more advanced features, I still really like the simplicity of this little system and the project as a whole, with the biggest challenge really only being the assembly. I really like the way that it integrates into my setup, with the base station living on my desk next to my audio rack, and the remote sensor nestled among some other things that live on top of my server rack. So finally, I can make sure that I'm not completely cooking my servers when I'm stressing out my new R720. Well, that's all that I have for you today. Hopefully you were able to at least enjoy this video, and maybe even learn a thing or two. In any case, I hope to see you next time. Goodbye.